Hi folks, this video is designed to go along with the class notes and example sheet from sections 2.1 and 2.2 that you should have in front of you. This is on polynomial functions, and it's just going to give an introduction to polynomial functions and some of the terms we use with those. So I start up here with an example of a polynomial function. This is a rather long one. Looks like it has 1, 2, 3, 4, 5, 6, 7 terms to it. Some things I'll point out. We just finished studying power functions. You'll notice that each term is a power function. All right. Power functions, remember, are the form of a constant times a variable such as x raised to a constant power. And that's basically what a polynomial is. In fact, we'll be writing that into our definition here. The other thing I want to point out is notice that all the exponents on the variables are actually whole numbers, okay? And this one here at 2, I think we saw, in the last, when we're dealing with power functions, we could rewrite that as, as 2 times x to the 0 power, and 0 is also a whole number. So these are positive integers plus 0, so the exponents are all whole numbers. Now the numbers that are multiplying the variables do not have to be whole numbers. They can pretty much be any kind of number they want to be. So here you see we have a root 7. Over here we have a fraction. Here's an irrational number, pi. Well, I guess root 7 is also irrational. So you can pretty much have any number multiplying the variable, but the exponent has to be a whole number. And so we're going to write that in as our definition. Okay, what is a polynomial function? It's not really, I should have written it as a sentence, but so you could think of it as a polynomial function is, okay, what is it? A sum of power functions. It's a sum of power functions for which each exponent is a whole number. Okay, some definitions you'll see, they'll say each exponent is a non-negative integer. Well, what are all the non-negative integers? They're simply whole numbers. Okay, whole numbers being all the positive integers plus 0. Okay, so that's why we say whole numbers, so that we include 0. So based on that definition, why don't we take a look at some examples of things that might be polynomials and identify which are and which are not. If you decide it's not a polynomial, then you need to give a reason, point out why, and generally it would be because you don't have a whole number for the exponent on one of your variables. So I will tell you right now, I think there are 2 in this list that are not polynomials. So try to identify which of those 2 it is, and then we can talk about why the others are. So pause the video and go through these yourself. All right, thanks for doing that. Let's take a look at these. Hopefully you felt like number 1 was pretty quick, right? We got a 2 for the exponent here. Of course, what's the exponent on x? It would just be a 1, right? And this would be 1x to the 0, so definitely a polynomial for that one. Going into number 2, I really don't see any problem. The fact that we have a root 3 here is not a problem. The exponent on the x is just a 1, right? Keep in mind that x is not inside the square root, so we're good, right? When you got to number 3, hopefully you were a little hesitant, because we do have x cubed in the denominator here. Yes, we could rewrite this, right? We were doing this with the power functions as 3x to what exponent here would it be? It wouldn't be a 3, because we've got in the denominator. If you said negative 3, let me see if I can turn this into a negative 3, then you are correct. And that would be why this is not a polynomial, right? Because we have to have whole number exponents, and negative 3 is not a whole number, right? Going over to number 4, this one can make a quick transformation. This is a polynomial. It's now, of course, it's just got one term. We'll learn that's called a monomial, okay? And this would be just 2x to the 0. So it is a polynomial, though, even though poly means many. We call it a polynomial even if it's a monomial. I mean, if we really wanted to, we could add in another term. We could say, well, okay, it's plus 0x squared, you know, and there we go. There's your several terms. But yeah, a single term is called a monomial. Because we didn't mention it here. This one here, which is 2 terms, right, is called a binomial. And of course, one with 3 terms is called a trinomial. Once we get above 3 terms, we tend not to use names for it. We just say a 4-term polynomial or something like that. All right, going down to number 5 now. You might have been thrown seeing the fraction again, but notice this time the x cubed is in the numerator and not in the denominator. So we simply have another binomial where this first term is just 1/3 times x cubed, right? All right, and then the last one here, I guess we've only found one that wasn't polynomial, so this one, number 6, must not be a polynomial. We're okay, I think, with the first term, but when we get to that second term, right, we have that square root on the x, which when we write it out as power functions, this would be 3 times x to the 1/2, and 1/2 is not a whole number, so we don't have a polynomial. As we move along here and take a look at the general form of a polynomial, it looks scary at first, but it's really, if you just look at it carefully, it's just adding up power functions, okay? We're using these little subscripts to just help us to note that this number a sub n minus 1 is different from this number a sub n, okay? And the idea is that n is the highest exponent, the largest exponent we have, and then we go down by 1. When we do that, this is called writing it in standard form, which we'll mention a little later. And so, you know, n might be a 5, so there'd be x to the 5th term power function, and then there might be an x to the 4th. There might not be. A sub n minus 1 might be 0, okay? And then we might have an x cubed term, and then we can get to an x squared, x to the 1st, and so forth. Of course, any of these a's could be 0, so we might not have an x squared term in them. This last one here, you'll notice, is a sub 0 times x to the 0, but x to the 0, of course, is just 1, so that's why we could rewrite it without an x on it. All right, so some terms that we have are as follows. We have what's called the degree of a polynomial, okay? So the degree of a polynomial is the largest exponent. All right, I'm going to write that. It's the largest exponent. And so in our general example here, the degree would just be n, okay, because that would be the largest exponent in our general form. So we might call this an nth degree polynomial. You know, sometimes we'll say it's a 5th degree, 4th degree. That tells us what the largest exponent is. The terms I've written out, you know, the terms are just each one of these power functions. So just writing them out. The coefficients now, those are simply the numbers that are multiplying each variable, right? So we would have a sub n, and then a sub n minus 1, and then a sub n minus 2, all the way down to a sub 2, a sub 1, and then I guess we could call a sub 0 a coefficient. It is multiplying x to the 0, but it also has a special name, as we will see. Yes, indeed, a sub 0 is, of course, what's called the constant term, right? It's the one term where the variable does not necessarily show up, okay? Now, the leading term, that is always the highest degree term, okay? A lot of times that's the term we write first, but it doesn't have to be, but it is the highest degree term. Okay, so in our example, our general example, it would be a sub n times x to the nth power. And it's a very important term, because, as we will see later, because it does dictate what happens for large values of our polynomial. So this is one reason we're paying a lot of attention to power functions, what their graphs look like. The constant term is also kind of important. We'll see pretty much, if you think about it, if you plug 0 in to your polynomial, all these other terms will become 0 and you'll just be left with your constant term. And that means that the constant term is the y-intercept, right, of your polynomial. All right, and then the last thing we mentioned is when we get a polynomial in standard form, that means we align the terms from highest degree to lowest degree. And so, the way we have it written here is this is in standard form, okay? Because the highest degree would be the nth degree, and then the lowest would be the 0. So having covered that, why don't you do some of this to the polynomial we started with. Why don't you first write it in standard form, okay? And then state what the degree is and what the leading term is for our polynomial f up here. Pause the video and do that. Okay, thank you for doing that. See if this is what you got. All right, so one thing you want to keep in mind when you rewrite or write a polynomial is making sure that the sign stays with the term that follows it, right? So I got a positive that stays with the 12x cubed, the negative stays with the 1/2 x to the 8th. So we have negative 1/2 x to the 8th, right? And then the minus here stays with the root 7 x to the 6th. Looks like most of the rest of them are positive, but they're going down in degree. Now, if you really wanted to, you could put in those 0. You could have in here, because we don't have the x to the 7th term, we could say, plus 0x to the 7th, but there really is no need to do that. When you skip over terms like that, that's fine. Okay. This is an 8th degree. I didn't ask for how many terms, but it's an 8th degree 7-term polynomial. All right. And the leading term is negative 1/2 x to the 8th. And as I was saying, one reason we're going to pay attention to that leading term is we can know, we're going to see later, we can kind of know that basically this polynomial is going to do the same thing that 1/2